Okay, good afternoon. So today we'll continue our discussions on I/O subsystem. We talked about PCIe. We talked about device controllers. So the next thing that we're going to talk about is accessing devices. So there are two ways to access devices. The first one is called IO map. Sorry, port map method and mechanisms. In this one, the IO subsystem has its own address bus. So there is no sharing of the same address bus between the memory and IO subsystem. So memory has its own address bus, and then IO has its own address bus. Now, for CPU to send requests on this IO bus, it has to use separate requests. So in Intel, for example, when you use in and out instructions, then you automatically send requests on the IO bus. So in particular, for example, if you send out 0x21AL, this means that you want to write the register here in this particular address, and because you're using out, we know that this request is going to be sent on the IO bus. If you had used store, for example, the same address, AL, this would send the value of this register to this address in memory. So load and store would use memory bus, out, in and out would use the IO bus. Now, this is not very common in modern architectures. This is, I wouldn't say modern, probably general purpose. So this usually is used in microcontrollers, in real-time systems, but not on general purpose. For example, computers and x86 computers. Okay, so what is really common is memory mapped I/O. So basically, I/O devices and the memory, they both share the same address bus. Therefore, CPU can communicate with both of them using load and store. Now, when a load and store is issued, the address basically identifies if this request should be sent to IO or if it should be sent to memory, because both of them use the same address bus. So IO devices in particular, if you remember, listen to a range of addresses that is assigned to them, and memory listens to a range of addresses that is assigned to it. And both of them basically are connected to the same bus. Here is an example. Let's put everything that we have seen together. We're looking at a display, assuming that it has a command buffer and a data buffer. So these are hardware storages on the device, on the display, and during the setup, we have mapped them to these ranges of memory addresses. So any load and store within this range would then write to these buffers on the device. So these are not in physical memory. These are on the device. So if you issue load and store, you're basically reading or writing to the storage inside your device. And let's assume that the registers are mapped to these two. So let's just in particular assume that there are two registers, a command register and a status register, and we have mapped them to these particular addresses, physical addresses. Now, When does this mapping happen? Usually during the BIOS setup, when the BIOS is setting up the system before booting the operating system, but in some cases it could also happen by the operating system at boot time. Now, let's assume that you want to change the display. So you send your the data that has to be processed. Let's assume that you have, some curves or whatever you like, some shading. So you first send, for example, your data in the data buffer, then you send your command sequence to the command buffer. So these basically means that you issue a bunch of stores, store whatever address, and then whatever data you want. Again, store the address, and this address is within this range with the data that you want. I guess here is command, and here is your data. So you first basically send everything that you need to these buffers. Eventually, you send a signal to the display by writing to this command register to tell the device to execute the commands. And potentially, you could indeed check the status, for example, before doing so. And if you remember, when we were talking about access control, I talked about this particular access control, which was write only. So no execute, no read, but just write. And that could, here you can see it, it could be used, for example, for this command register, this or this command buffer. So this is something that you just write, or this display buffer. So you just write to these addresses, because you're basically writing to the device. So you should not read it, because you don't know what the device is going to do with those. This a status register, you probably want to have read and write potentially, or just read only access, depending on the device and how it's implemented and so on and so forth. Now, this is a recall. We saw this in early lectures. There are two ways to transfer data between CPU and the device. One is programmed I/O. So with this one, for every byte of data that we send to the device, we're using CPU cycles. So basically, let's assume that you want to write a gigabyte of data to your GPU, to your GPU's memory, for example. You just read from your own memory and then write the data that you just read to your GPU using stores, for example. This is simple hardware, and not much requirement to implement any additional hardware. It's also easy to program, right? However, it's just has a lot of overhead. You're consuming a lot of CPU cycle for your I/O. The other alternative is to do direct memory access, DMA. Basically, your driver sets up the transfer, tells the DMA engine to copy a certain range of from a certain range in physical memory to the device, or from the device to memory. And then the DMA engine does that while the CPU is doing something else. Once the data transfer is done, the device can interrupt the CPU, telling the CPU that the data is completely transferred. Now, when it comes to PCIe devices, usually each one of them has a DMA engine, or bunch of DMA engines, not just one. Now, these are proprietary DMA engines implemented within the device. So for example, your SSD probably has a bunch of DMA engines. Your NIC card has a bunch of them. Your GPU has a bunch of them. So that when the device driver starts running, instead of communicating with this shared common DMA engine between all IOs, it just talks to the proprietary DMA engine inside the device, giving that instructions, and then that DMA engine inside the device starts the transfer to or from the device. And once the data transfer is done, the device will interrupt the CPU. Now, so and this is basically possible because we have this peer-to-peer communication between all PCIe endpoints, and memory is one endpoint. So every device can basically send packets directly to the memory. So this is basically brought to us by PCIe protocol or PCI protocol. Is engine a synonym for controller? Yeah, you could imagine that. Yeah, it's just a hardware controller that deals with DMA requests. Okay, now let's talk about memory protection. Historically, oh, I got another question. Is it the norm that there is a memory bus per CPU core? There is a memory bus, yes. So you usually have a single memory bus. I mean, if I go up, this is usually what you have. So there's the memory bus that is connected to your memory controller. Now there is a bus that connects your CPU to memory controller. There is a bus that connects IO controller to memory controller, and so on and so forth. Okay. So historically and traditionally, you had your IO devices being allocated a contiguous range of addresses. And this was the case because you didn't want to have a lot of hardware implementation for your device. You just get a base address and then a range. So for example, for the case that we saw, there was a command buffer for your display or data buffer for your display. You get a base address and a range address. So where is this buffer mapped to in physical memory? The same for your registers. You would get a base address and a range address to know where your registers are mapped to, using the address in the address bus. Now, again, historically, we would allow the devices to directly communicate with physical memory. So they would use, if let's say your device wanted to DMA to memory, it would use physical addresses to read, for example, from memory or write to memory. Now, the positive point, the upside of this was performance, because there was nothing in between the device and memory. The device could just use physical addresses to access memory. The downside is twofold. First, it reduces protection, very important. If your device is malicious, well, it has access to all physical addresses. It can read or write from or to addresses that are that are protected. I mean, we don't want it to access, but there's nothing preventing your device from accessing those. The second problem with this, like a combination of the first one. The first one is a fact that, you know, our devices have a base and bound kind of implementation when it comes to address. Now, if we have to allocate physical memory to them or physical addresses to them, then this basically kind of restricts the operating system in terms of how it can manage physical memory, because you might have enough physical memory to allocate to your device, but it might not be contiguous. And this could lead to fragmentation, external fragmentation, for example, because your device cannot use, you know, separate and divided ranges of physical memory. It has to have contiguous memory range. Now, to address both of these, in new architectures, we do the same thing we did with CPU, which is we make devices use virtual address, and then we translate virtual address to physical address. Now, the downside of this is performance, obviously, because very similar to what we did with CPU, now we have to translate addresses when the device wants to go to memory. Now, the upside, however, is that both of the problems that we had above are addressed. First of all, we have protection because, again, if the device only can use virtual address, then you can restrict the access of your device to whatever you map those virtual addresses to the physical memory. It also gives you flexibility because you could have, you know, different physical pages that are not contiguous, but then you can allocate a contiguous virtual address range and then map that contiguous virtual address space to separate physical pages that are not necessarily contiguous. Now, let's look at this this diagram in this slide. If you remember, the job of translating addresses for CPU was with memory management unit, MMU. So the CPU would create virtual addresses, and then MMU would turn them to physical address, and that physical address would be sent to the memory controller, and then eventually to the memory to read the data. Now we can do the same thing for our I/O devices. The unit that was added is IOMMU. So it's doing exact same thing. So this allows devices to generate virtual addresses, and the IOMMU maps those to or translates them to physical addresses to then go to memory. Now, the same process that happened with MMU, where the operating system was in charge to set up page tables, happens with IOMMU. So depending on how you want to set up the, like, what virtual ranges are assigned to each device, the operating system is responsible to set up page tables that will then be used by IOMMU to translate physical address to virtual address. So this is Intel VTD and AMD VI. These are new technologies. In ARM, if I'm not mistaken, it's called SMM. What is it? In ARM, it has a different name. It's not IOMMU. It's gosh, I forgot. It's System MMU support. It's SMMUS, if I'm not mistaken. Oh, it's called SMMU. Yeah, System Memory Management Unit. That's the name for ARM architecture. But in x86, it's called IOMMU. Okay. Now, when it comes to PCIe devices, there are some challenges. The first one is the same way that you have proprietary DMA engines implemented inside your device, you could have TLBs implemented inside your device. What does that mean? So TLB, if you remember, was a cache for virtual to physical address translation. So once we go to MMU and translate our virtual address to physical address, we probably want to cache that translation so that next time we don't need to translate it. The same happens with IOMMU. IOMMU has its own TLB to cache the translations, but PCIe allows the devices to have their own TLB. So if your device goes to IOMMU to translate a virtual to physical address, it could cache that translation. And later on, when it wants to access the same address, it could use its own cache translation, go to IOMMU and say, I don't need your translation anymore. I already know the translation. Let me go to memory. And this is possible in PCIe or in PCI protocol. This is allowed. Now, this is a security risk if your device is malicious, because, well, you can just bypass IOMMU and say I have the translation, but maliciously use a physical address that is not supposed to access. The other security risk that PCIe protocol allows is peer-to-peer communication between devices. Now, what could happen is your device could potentially take control of another device by sending or reading sensitive data from your excuse me. By corrupting the other device, because it can just send requests to another device and write corrupted data to that other device, or read sensitive data from the other device. Now, fortunately, there is a solution for both of these two, and the solution is the same for both. So with one solution, we can actually address both of these two challenges. The solution basically is called Access Control Service, which is, again, another feature that is enabled in PCI protocol. And what it does is it forces all PCI requests to go through IOMMU. And it basically makes sure that nobody can bypass IOMMU. Now, this comes with performance cost, because basically we're preventing devices to implement their own TLB. I mean, even if they do, we're not going to allow it to be used. So all the memory requests have to go through IOMMU. We don't trust the device to say, I have the translation before, I have cached it. We say, sorry, just give me your virtual, your request in virtual memory, and then I send it on your behalf to memory. So that's first. Second, we also don't allow devices to communicate directly to another device by bypassing the IOMMU. So if you remember, if I go back to this picture here, this PCI device could send a request to this other PCI device without going to this root complex where the DMA, where the IOMMU is implemented. So with access control, we don't allow this communication to go through this. We force the communication to go first to the root complex and then come back to the other device. And inside the root complex, the IOMMU basically checks and validates the request. And this prevents malicious hardware to attack other hardware. So I got a question here. What's a hub? Basically, this is memory controller and IO controller, if you're asking about here. So it's based on the north and Southbridge architecture. If you go back there, you will see it says memory hub or memory controller. It's just synonyms. Okay. I'm going to just briefly talk about IO subsystem performance. We probably won't have time to cover all the slides. I cover as much as I can, but then we'll have to skip over some of those because otherwise I won't have time to talk about file systems and probably reliability. Okay, so we are going to consider a very simple model of IO subsystem. In this model, the device driver is going to create IO requests. Then the IO requests are going to be queued in a single queue. And then eventually the IO controller, the device controller, is going to dequeue requests from this queue and start processing them. Now, in reality, this model is not accurate. So in reality, once your device driver generates the request, actually before that, so when you do a system call, for example, to read or write, for example, to a file, this gets queued initially in IO queues. That's a software queue. Then once this is processed inside the software and a hardware request is generated, this request is usually sent to the device, and then there are queues inside your device to queue this request for it to then eventually be processed by the IO controller. So this is a very simplified version of what happens in reality. But for the purpose of having a first order analysis of IO subsystem, this should be enough. Now, with this model, the latency of each IO request is the time that IO request waits inside the queue. So you spend some time here waiting, and then you spend some time here to process. So once the IO controller gets the request, it has to process the request. And then finally, you get to be transferred back to the, does this have double R, I assume, to CPU, for example, or from memory. So it has three parts. All of this would be the latency. So the summation between these would be the latency of your request. Now, the overhead is basically this. This is called overhead. So right before you start transferring your data is overhead. So the time you spend waiting, and then the time that the controller processes your request is called the overhead of this model. And then eventually the transfer is the part that you're interested in. Now, the throughput of your system is basically the rate at which you serve these requests. So if we look at here and see how many requests per second we're processing, that would become our throughput. Now, usually when we talk about throughput, there is a peak throughput. Sorry, when you're talking about throughput and you're talking about I/O devices, people usually care about data transfer rate. How much data can you transfer? For example, with your NIC or with your GPU or with your SSD, people are interested in your data transfer rate. Now, the maximum data transfer rate depends on two things. First, depends on the bus that connects your device to the system. Now, for example, with PCIe devices, you can per lane you can go up to almost 4 gigabit per second. Sorry, gigabyte per second. With other protocols, this might be less. The other portion or the other component that is important to identify the peak latency, sorry, the peak bandwidth, is how fast is your device itself in transferring data. You might have a really fast data bus, but your device is slow in sending or receiving the data. For example, the old magnetic disks, basically your hard disk drives, they are limited in how fast the disks are rotating. So even if you give them a PCIe bus that they can send, gigabytes of data, you usually are limited in megabytes of data because that's how fast you can transfer data off of your disks, your platers that are rotating. Now, overall, you're limited to whichever is slower. So if the device is slower, your peak bandwidth would be identified by the device. If the memory bus is if the bus that connects your device to the rest of the system is slow, then you're limited by that bus. So whichever is the bottleneck, that would identify your peak bandwidth. Now, peak bandwidth is not usually the most important factor in your system. Usually, we're interested in the effective bandwidth. So what is effective bandwidth? Let's say I have this really cool SSD, but I'm not using it at all. So what is my effective bandwidth? It's 0 because I'm not using it at all. The effective bandwidth is usually related to how much data we're sending or receiving. So to calculate the effective bandwidth, we first need to have a we first need to model latency. So what is latency? We saw it in the previous slide. Latency was the overhead plus data transfer. So what is data transfer? Well, if you are transferring n bytes, you divide that by your peak bandwidth. That gives you the time it takes to transfer your data. Now, your effective bandwidth is how much data you're transferring divided by your latency. Now, as you can see, if latency is 0, if your requests do not wait at all, if there is no overhead, then your effective bandwidth is equal to your peak bandwidth, if n is not 0. But usually, overhead is not 0. I mean, realistically, overhead is not 0. You're always spending some time processing the requests or queuing the requests. And the time that you're spending for that, you're not spending on transferring data, and that brings your effective latency down from your peak latency. So your peak latency is always the highest achievable bandwidth in your system. Now let's put this together. So this is what we saw last in the previous slide, latency equals overhead plus n divided by p. So here O is overhead and p is the peak bandwidth. Now, what is effective bandwidth? Well, give me a sec. The effective bandwidth is, as we saw, the number of bytes that we are transferring, which is n, divided by the latency, which is O plus np. So if you just move around everything, you get to effective bandwidth is equal to peak bandwidth divided by peak bandwidth times O divided by n plus 1. Now, as you can see, this effective bandwidth depends on n. So does the latency. So latency is a linear function of n. The more data you want to transfer, the higher your latency is, obviously. The same with effective bandwidth. Now let's put n equals O times p in this equation. So it would become p divided by p times O. Now instead of n, I'm going to put O times p here, plus 1. Now obviously O cancels out with O, p cancels out with p. This becomes 1. And this whole thing becomes p divided by 2. So my effective bandwidth becomes half of my peak bandwidth. So if I'm transferring this much data, then my effective bandwidth is half of my peak bandwidth. And this is usually something that you can calculate. Here is an example. Let's assume that you have this network card, for example, that has a peak bandwidth of 1 gigabit per second. Now, if the overhead of your device is 1 millisecond, so first of all, let's look at this graph. So here, this is n, how much data you're sending. The blue curve is your latency, which should be a linear function of n, which is, as you can see, the blue curve is a linear function of n. As n increases, the latency increases as well. And then the red curve here is your effective bandwidth. So in this particular example, to get to half bandwidth, half of your peak bandwidth, you can just send n equals overhead, which is 1 millisecond, times your peak bandwidth, which is 1 gigabyte per second. Now divide this by 8 bits per byte, and that gives you some 120K bytes. Now, if you have a slower device, a device that has higher overhead, 10 millisecond, then the number of bytes that you need to send to get to the same effective bandwidth is 10 times more, as you can see. So as you can see here, the effective bandwidth curve is an increasing function of your data that you're transferring. The more you transfer, the higher your peak bandwidth is. Sorry, the higher your effective bandwidth is. But then depending on the overhead, this curve changes. So when your overhead is too much, then the curve is like this. When your overhead is less, then this curve goes up faster. So what are the contributing factors to overhead? So as we discussed, the main two components are the wait time in the queue and then the controller, the processing in the controller. So we can focus on this first part. because this second part is usually by the device, right? The device. Oh, so going back, somebody is asking, so greater overhead is better? No, it's actually vice versa. More overhead means lower peak bandwidth. It means that you need to send more data to achieve the effective bandwidth that you could have achieved with lower data when the overheads were lower. So don't forget, we're usually not sending much data. So we want the effective bandwidth to be high, even if we're sending a little bit of data. So if the overhead is high, then for the same amount of data that you're sending, your effective bandwidth will be lower. So basically, if I were to say this, fix your data size, the higher your overhead, the lower your effective bandwidth. So higher overhead means lower effective bandwidth. Okay, so again, when you analyze your overhead, you see that it has these two components. One of these two components is basically the device. We don't have anything to do with it. The other overhead here is your queue. The software might have something to do with it. As I said, for example, your I/O requests get buffered in the software. Now let's analyze a little bit. Again, I'm not going to go deep into this one. In fact, I am going to skip all of it. So just this slide. So usually when you look at the wait time in a queue, this is as a function of the data that you're sending to the queue, the function of how much you're utilizing this queue, how much data is being sent. So this is the percentage of maximum possible throughput. So if, let's say, if you're at the front of this queue, you're processing 10 requests per second. Now, if you send 9 requests per second, then your utilization is 90%. If you're sending 5 requests per second, your utilization is 50%. So here the utilization is on the x-axis, and the wait time is on the x-axis, on the y-axis. Now, this usually is correct for most of the queues that you will see in your life. The higher the utilization is, the higher your wait time becomes, obviously, but the increase is not linear or sublinear. It's actually exponential. So as you increase your utilization, as you get closer and closer to your maximum throughput, your wait time increases exponentially. And at some point, it actually blows up. So usually you cannot reach the maximum utilization. Usually, depending on the parameters of your queue. Okay, so I'm gonna actually skip over these parts. If you're interested, just look at the slides. They should be self-explanatory. And there are actually other resources if you're interested to read for queuing systems. cannot talk about these because we have other stuff to cover. Your book actually has some good explanations on this, so if you're interested, definitely take a look at the book. But I have to skip over these. Right. So basically, at the end of these slides, I actually showed this mathematically, how wait time is a function of utilization. So in this equation, rho is your utilization, and as you can see, when rho is equal to 1, the denominator becomes 0, so the wait time goes to infinity. So again, unfortunately, we don't have time to talk about this and model this mathematically, but if you're interested, definitely take a look. Okay, so where are we on memory? On I/O. We talked about I/O subsystem, the general view of I/O subsystem in the kernel. We briefly talked about I/O performance. At least we talked about the definitions of latency, throughput. Now, the last thing that we're going to talk about with I/O is basically storage devices. Now, this is a topic that historically have been discussed in operating system courses for some obvious reasons, because you know, we care about processing, we also care about data storage. That's why we spend so much time talking about memory, where we store our data, and well, beyond memory is your permanent storage. But these days, all the other I/O devices are becoming also equally important. So there is a lot of research in making our network devices and network subsystem faster. Obviously, there is a lot of industry interest in making, for example, your GPUs faster and more powerful. There are other, you know, I/O devices like a specialized hardware for, if I am to give an example, for TPUs, for example, tensor processors or FPGAs. Unfortunately, we don't have a advanced operating system course in ECE. I believe CS has an advanced operating system course. I don't know how frequently that course is being taught, and I definitely don't know if you know, advanced I/O is being covered in those courses. But this definitely is an area that people are looking very actively, both in industry and academia. I think 1 or 2 years ago, the best paper award in one of these top operating system conferences went to a method that was making I/O subsystem faster. So anyhow, let's dive into this stuff devices. I'm going to talk about two different technologies in implementing I/O devices. Sorry, in implementing storage devices. The first one is the magnetic storage, and the second one is the flash storage. Magnetic storage is usually larger capacity, and it's usually cheaper, but it's slower and more faulty. The flash storage has medium capacity, but it's more expensive, and it could wear out. So we'll discuss these. Now let's start with magnetic disk. My guess is like within 5-6 years, nobody will talk about magnetic disks anymore. But right now, some usage still exists for these magnetic disks. They will eventually disappear as flash disks become more mature and more available, and the price on those go down. But here we are at this point. At least, like there was a Google paper some years ago on how Google is using these magnetic disks for their archive because they're cheaper and they have more capacity, and they were talking about making it faster, the way they were managing these disks. So the main components of a magnetic disk is the platers. So these are these disks that are rotating. Now, on both sides of these, you can store data. The way you read and write is through these heads. So there is an arm that has the head at the top of it, and this arm can move back and forth. So it could go all the way to the inner circles of your disk to all the way to outer circles of this disk. Now, each circle on the disk is called a track, and each track is divided into sectors. Now, again, we have basically two sides. So each track has two sectors, one top and then one bottom. And then all the tracks for the same diameter on all the plates, all the platers, is called a cylinder. Now the disks are rotating, and do I have anything left to talk about? No. Okay, so the unit of transfer is sector, as I mentioned. Each track is about 1 micron, and to just give you a point of reference, the wavelength of light is 0.5 micron. So it's extremely thin. And again, human eye can only see resolutions about 50 microns. So a typical disk of 2.5 inch has more than 100K tracks. Now, because these are very thin, there is always there's always the possibility that the head might move and not be precisely on top of the track that you want to read your data. So to avoid reading from another track or writing to another track, you usually have these spaces between your tracks, the empty space left as a guard between neighboring tracks. Now, area-wise, if I look at the half of this, so this area inside is usually a fraction of the area outside. So this outer half is much bigger than the inner half. So sometimes, you might actually just prefer to use this half and forego the other half. Now you will see why this is important and why this is an optimization, because if you focus on this half, then your head can just move half of the distance and not go to this inner half. And that minimizes the movements of your arm. And you will see that that could speed up your requests. Okay, I talked about Google. Let's see what is the overhead of reading or writing from or to the disk. So let's assume that your arm is initially here. So the head is looking at this track, this inner track. If the data that you want to read is in this outer track, then you have to do two movements. The first one is for your arm to seek to the outer track. So this is called seek time. This is the time it takes for the arm to move towards the outer track, so moving back in this case. And then once that happens, then you have to wait for the disk to rotate so that the sector that you're interested in comes under the head. And once the head is on top of the sector, then you can start transferring your data. Now, to put this into perspective with the I/O subsystem performance model that we saw, you're going to have your disk latency being the time you spend your requests spent in the queue, the time your requests are processed by the HDD controller. Once you have that all done, then from then you have to pay a seek time, a rotation time, and then a transfer time. So this becomes your disk latency. Now let's look at this with some examples. Let's make some assumptions. Let's assume that there's no queuing or controller time for now. So both of them are 0. Let's assume that the average seek time is 5 milliseconds. Depending on how you seek, so seeking, for example, from this sector to this, from that track to this track, obviously is longer. So than you wanted to seek to another track in the neighboring tracks. So that would be faster. Let's assume that the average seek time is 5 milliseconds. Let's suppose that our system is a 7,200 round per minute hard disk. Now, the time for a full rotation is basically, well, you have 60,000 milliseconds per minute, and then you're having 7,200 rotations per minute. That gives you about 8 millisecond rotation time. So this is the time that it takes for a complete rotation. Let's assume that your peak bandwidth is 4 megabytes per second. Now, if the sector size is 1 kilobyte per second, then the time that it takes for you to transfer one sector is about 0.24 milliseconds. Now, with all of that, let's assume that you want to read a random sector from your disk. So you have to pay a seek time, which is 5 milliseconds. You have to pay a rotation delay. Now, for rotation delay, I'm using half of this because 8 is for full rotation. Average rotation becomes half of this. Sometimes you have to have a full rotation. Sometimes your data is right next to the head. There is no need for any rotation. So on average, it's going to be half rotation. So 4 milliseconds. And then let's say we're transferring the sector, so 0.24 milliseconds. Now, this gives you an approximate latency of 10 milliseconds. So if you're transferring one sector of size 1 kilobyte, and this is taking 10 milliseconds, so this is your effective bandwidth, which is around 100 kilobyte per second. Now, let's assume that you want to read a random place on the same cylinder, on the same track. So you don't need to seek to another track. You just need to wait for the disk to rotate. Now, on average, you're going to just pay the rotation delay and the transfer delay. That reduces your latency to 4 to 5 milliseconds. And by reducing the latency, we're achieving higher effective bandwidth of 200 kilobytes per second. Now let's take this example one step further. Let's assume that not only I don't need to move tracks, I don't need to wait for rotation, I want to just read the next sector. Then I'm not going to pay the rotation delay, I'm not going to pay the seek delay, so I'm just going to transfer. And at this point, I have achieved my highest possible effective bandwidth, which is exactly the same as my peak bandwidth, which is 4 megabytes per second, because I'm just transferring data. I'm not paying any overhead. So obviously, we will come back to this when you have sequential reads, meaning that you're reading from the same sectors. Sorry, not same sector, the next sector on the same track, then you achieve the highest bandwidth. So usually when you buy these hard disk drives, they give you bandwidth for sequential reads. They also give you bandwidth for random reads. And as you can see, the bandwidth for sequential read is different from bandwidth for random reads. Now, because of all these physical movements that your hard disk drive has, and it's the sensitivity of bandwidth to where the data is, usually there have been, historically, there have been a lot of efforts to optimize data placement, so where you put your data on the disk, and also request the scheduling. So we'll talk about request scheduling in a bit, but let's say you have your ARM is here, but then you have requests all over the disk to read these sectors. You probably want to sequence these requests so that your ARM movements are minimized, and potentially your rotation as well, to maximize your effective bandwidth. So there has been a lot of work in optimizing all of this. So let's look at some more examples. Let's look at 500 random disk reads, and let's assume that we're looking at these in a FIFO order. So first request in, first request, first response out. So in the previous example, we saw that each one random disk read takes on average about 10 milliseconds. So if you have 500 of them, you're going to spend this much time to do all of those. So now you can actually look at 500 sequential disk reads. So for the first one, you are going to pay the seek time and the rotation time, but then all the rest of them, all the rest of the requests, you are only going to pay for the transfer. So one seek time, one rotation time, and then from then on, you're only paying the transfer time. So you can see that the latency dramatically decreases from 4 seconds to almost 0.1 second. A 40x performance improvement. And this will show itself in your peak in your effective throughput. Obviously, you brought down the latency, the throughput goes up. Now let's look at this example. How large your transferred data should be to achieve 80% of your maximum disk transfer rate. So this is kind of like a tricky question. Now we know that we can get high throughput if we read from the same sectors, from the sectors on the same track. So let's assume we don't know how many tracks we need to read. Let's assume that we need to have R rotations to read all of our data. We don't know how much data, so we don't know how many rotations we need. So let's assume that we need R rotations. Basically, we need to read from R tracks. Now, what is effective bandwidth? Well, effective bandwidth is the data size divided by latency. And going back to the equation we had, it's equal to peak bandwidth times transfer time divided by latency, obviously, right? So how are we going to use this? So all we need now is for this to be 80%. So we want the transfer time divided by latency to be 0.8. Now, what is the transfer time? Well, the transfer time is basically our rotation time, right? And multiplied by R, because we're reading from R different tracks. So it's going to be R times rotation time. Now, in this particular example, the rotation time was 8 milliseconds. Here, we're not using the average rotation time. We're using the full rotation time because we're reading full track. What is the latency? Now, we're assuming that we have to seek to a random track. So it's going to be the seek time. We're going to pay the seek time. We're going to pay the transfer time as well. So that's our latency. So putting everything together, we get we have to now solve for R. The only variable here is R. So if you solve this equation, R becomes 2.5. So the data that you want to transfer is 2.5 times 8 millisecond. Assuming that you can transfer 4 megabytes per second, that's your peak data transfer. You're going to transfer 8 kilobytes per second. Sorry, 8 kilobytes of data. I got a question here. Why is it R rotations instead of R tracks? Right, so they're the same, right? R rotations means R tracks, because on each rotation we're reading one track. Why is rotation delay 0? You said R rotation time, where rotation time is 8. Right, because we're assuming that the moment the head comes on top of the track that we want to transfer, we start transferring. So we're not going to wait for a particular sector to come under the head. So right after we get to the track, we start transferring. So we're just paying a rotation cost, sorry, the seek time, and then the moment we get to the track, we start transferring. And the transfer time is basically the rotation time. And while we're rotating, we're also sending data. So our transfer time is our rotation time this time. It's a little bit, you have to think about it, but all it means is the moment you get to the track, you start transferring. You don't pay any rotation cost. Remember, the rotation delay was the time you wanted to wait after the head gets to the track. You want to wait for the particular sector that you're interested in. Now, we're not interested in a particular sector. We want to send the entire track. So any of the sectors come under the head, we can start transferring. So we don't pay any rotation time. Now, the last piece is the transfer time. The transfer time, because we want to transfer the entire track, the transfer time is the rotation time. So seek time is the same as rotation time, no? Okay. So for the remaining time that I have, let's see. I guess we might have time to talk about sorry, I got a question here. So what is the question? The question says, don't you need 5 times R as well, since you are transferring R tracks? I don't get it. Why 5 times R? I have no idea. We're assuming that the tracks that we're transferring are neighbors, so we don't pay. So we go from one track to the neighboring track, so we don't have multiple seek times. We have one seek time to get to the first track, then we move a little bit, so we're not going to move to another. We're going to just move to the next neighboring track, which we're assuming that the cost of it is almost 0. And then we transfer that track, and then we move to another track to transfer. So the tracks, these R tracks, are neighbors, so we don't pay any seek time. We just pay the seek time for the first one. Okay, so as I said, due to all this sensitivity to how the arm is moving and where the request, which sector the request resides, there has been a lot of work on making these controllers, the HDD controllers, smart and intelligent. So here are some of the optimizations that have been put to practice. So there is this sector sparing. This is when you have, I don't know if you guys have seen this, but back in days when HDDs were very common, often you would get this blue screen with window that would tell you that you have a bad sector. And that what that means is that one of the sectors that you had information was corrupted. So you had this sector sparing, which the hard disk controller would reserve some of the sectors, basically not presenting them to the operating system or to the entire system to be used for when these backed sectors happens, and then the controller would internally figure out that this sector has been corrupted, and then it would remap the corrupted sector to one of these reserved sectors. This was called sector sparing. The other one is the sleep sparing. You sometimes, again, it wouldn't be enough to map a single sector somewhere else. Like, so let's assume that a sector here has been corrupted, or a bunch of sectors here have been corrupted, and the spare sectors that you have are here, right? So you might, if you just map this guy here in one of these sectors, then what happens is, let's say you have a file that is mapped to all these sectors here. Now your head has to come here, start reading until it gets here. Then the head has to seek to this track to then read this data here, and then go back to the initial track to read the rest of the data. And this basically seeking backwards and then seeking forward adds a lot of latency. So not only you might want to move these sectors that are corrupted, you probably want to move the entire file somewhere, right? The entire sectors. So that this is another optimization that you might want to do, slip sparing. The other one is track skewing. This one is interesting because sometimes by the time that you're done reading one sector, transferring one sector, the next sector has already moved from the head, right? So let's say you read, so these are the sectors on the same track. So let's say that the head is here, you read this sector, you cache it, you want to send it. By the time the sending is done, the head has moved over this one and it's now here. Now, if you number these sectors 1, 2, 3, now that you're here, you have to wait for another rotation for 2 to come back to be able to read 2, because you've already missed 2. With track skewing, the device, the memory, the hard disk controller would number these sectors differently. It would probably number them 1, 2, 3, 4, and then come back and number these guys in between, so that you go over them without missing that sector. So next sector is 2 sectors from the one that you just read, and so on and so forth. There are so many different optimizations that are implemented. So here is an example of a current HDD. I mean, this is not that current. This is for 2018, and then you can compare that to a 1986 machine, or sorry, device. So this particular one has 14 terabytes. The RPM usually is the higher end is 7,200 rotation per minute. They usually have this cache size inside the device. So this is, you know, if the transfer rate is lower than the reading rate, so if you're limited by your bus, so if the device is very fast, but then the rate of transferring data using the bus is slow, then you can buffer the data that you read in your cache, and then eventually transfer the data back to your device. So they had these caches on the device. This cache also could be used vice versa. Let's say if your bus is too fast and your device is very slow, then if you want to write, you can first write to the cache and then eventually write the data in the cache to the sectors. So either way, right, the cache could be used. If one of the, it's kind of like a buffer between the device and the data transfer from the CPU. Here comes the maximum transfer rate that we talked about. This is the transfer rate for the interface that you're using. SATA gives you the highest end would be 6 gigabit per second. This is the size of your sector. This is the average seek time. You usually get this information if you look at the data sheet of your device. This particular device has 8 platers and 16 heads. As I said, each plater has two sides, so you can read both sides. Yep. So that's that. So we'll stop here. On Thursday, we continue our discussion, hopefully ending this section and starting the file system. Take care, be safe. Talk to you on Thursday. Bye.